Hello, everyone, and I'm Carmelo Emmanuel talking about radio astronomy of the senior project I've been doing in September, and I'll be passing it to my advisor, Dr. Hassel, when I graduate in May in 2020. And what we've done in the beginning of the year of 2019, we've built a new receiver for the 21 centimeter telescope. On the left, that's what it looked like right in the beginning, and on the right is what the end result was of after the wiring, soldering, and all the major connections needed. Here's another view of our receiver, and throughout this PowerPoint, I will explain what each component of the receiver does and how it works. So start things off, the regulator. It's consisted of two capacitors, 1.1 and the other is 0.2 microfarads. What this little circuit does is that it creates a constant 12 volts of DC to power the amps component, and it gives us a constant DC voltage. So when we plug it into the wall, the voltage doesn't fluctuate. Next is the bias T. That's right after the regulator. So the bias T on our receiver is on the left. And what this does, it goes to up the wire to the Viper, shown on the right side is what our Viper connection looks like. And when the 12 volts goes up to the Viper, it powers that bias T. And when it comes back down the line, that's where the actual wave is coming from the Viper. Next is the amp. This is what the regulator is powering. And since we have very, very weak signals from space, we can barely see it, these amps makes the signal stronger so that we are able to view it and get an accurate analysis on our results. And you'll see this later in the PowerPoint. We have a couple graphs based on our Milky Way Galaxy. The next component we have is a filter. Small little component, but it's much needed because it takes out any unwanted data that we have. For example, if we have like frequencies that we don't need to measure, that won't be included in our data and give us a totally different result than what we were expecting. So it's kind of nice to have this filter take out anything that's not needed. Next, it was the software-defined radio, which was AirSpy. This does the processing of the graph. So instead of manually coding it out in MATLAB or Python or any other language, this AirSpy did it instantly and created the graph and put it on our computer almost instantaneously. So this AirSpy saved a lot of time creating the graphs. Going on to the results. What we have here is our Milky Way Galaxy, our 21 centimeter radio telescope is set to measure the center of the galaxy, which is pointed south at roughly 15 degrees. And what exactly it's measuring is the frequency versus the intensity. And we have a few graphs showing what it's like throughout the day, measuring it throughout the day. One important graph that we have here shows the Doppler shift, which is 20 kilometers per second. So throughout the day, this graph will change. But at this point in time, it was roughly 12 o'clock p.m. in in September or October. So we got this graph and this narrow peak on the right at roughly 100 kilometers per second, the Doppler shift. It's bad data. There's a few things it could be: a cell tower, other frequencies. But what we're really looking at is where it was at 20 kilometers per second on the Doppler shift, because this shows the highest intensity and the highest frequency of the center of the galaxy at that time, which was roughly at, I'd say, probably 24 Kelvin. Next, we have our another data, which is based at like 12:30 p.m. It's very similar to this previous graph that we have here that we were just looking at with the Doppler shift. This is just a graph it was amplified based on the results, so we can get a better look at it. See, now we can see that the highest peak at 20 kilometers per second is more like 18 Kelvin instead of my previous guess, which was 24. So as we can see, the amps in our receiver help significantly get better data. Next data off of our amps was at 4:30 p.m. As we could see, as the day moves on, the intensity and frequency of the graphs change. And this, as we were trying to get early on in the year, was a waterfall graph to show like the different color ranges from dark blue to red, where dark blue is the lowest intensity and red has the highest intensity. We're having trouble coding that up, but going on into 2020, I was able to do research at home and gather this waterfall image. I'll show you later in the graphs, later in the PowerPoints. Now going on to this year, 2020, due to this pandemic, I had to continue my research at home, and I have my advisor sent me a home software-defined radio system, hooked it up to MATLAB, USB, programmed a little bit of code to find different frequencies, different types. What we have here on this screen was just a basic simulation to get things started, to see if the program worked, any troubleshooting issues would be clean for the further research. So what we have here on the right is the graph, and on the left is our MATLAB code used to create that graph. This graph, you don't really get anything. You don't see anything we encounter. It's just a basic simulation to see if what we coded works. And if there was any issues, this is where the troubleshooting would start, and hopefully things would be cleared up. Next, what we have is high value frequency. We got the spectrum analyzer and this waterfall graph I was talking previously about. And what we have here is, with this high frequency, we can see at 0 is where the highest frequency is on this waterfall graph, because the red line going down, that represents the highest intensity, and dark blue, which would mean the lowest intensity. And since we have a very low values of low intensity, and it's mostly high to medium intensity, this is where the high value frequency comes into play, because it's very vibrant colors: the red, the yellow, and the light blue. But then there's also low value frequency as you can tell, there's a difference in the analyzer, the shift up on the high value and the shift down on the low value. And with this at 0, you get very little yellow, and that's the highest point of the frequency that we get on this low value. As you can tell, everything around it is dark blue to light blue, and that's where the low value comes into play. And this red line going down corresponds with the highest peak of the spectrum analyzer. Next, what I've found is the FM radio stations. And what we have here, what's not that's not blacked out, is based on where I live and the different radio stations that came through. As you can see, the high intensities of the waterfall correspond with the highest peak or one of the highest peaks in the spectrum. And this shows that the signals were coming through and I was able to get a clear sound out of it and nothing was broken up. And this signal analysis, what we have here is that it's between like 88 megahertz to like 107 megahertz. So in the middle, it's roughly 98.7 megahertz. On the left, it's like 93, 92 megahertz. And on the far right, it's like 107.3, I believe, megahertz when I collected this data. And these different bands represent the high intensity of the radio. Next, simulation I've done is UMTS. For people who don't know it, that's the Universal Mobile Telecommunication System. This is a mobile cellular system for networks based on the GSM standard. And this is just a general international telecommunications system that many people use. And what this is, the frequency it ranges from is like between 915 and 935 megahertz. It's a lot higher compared to what my FM radio stations were, which was just like 88 to 107. So the data I was looking at is based on the high intensity, which starts where the black section ends and all the way to the right. This is all the high intensity values that I was looking for. Because scrolling through the channels, I was trying to find good data which would be accurate to read. And with this, with the UMTS, it gives us like they're like based on distinguished codes and like time slots is where like when you could basically hear it, and it navigates through the mobile region based on this region it'll be different for other people. And this was the continuation of my project. I got further research done. I was able to get the waterfall data on like the start of my project, and this was based on the software-defined radio using MATLAB. And with this textbook I was given, it's very easy to follow. Everything's like step for step, so if you have any troubles, it's easy to troubleshoot. It makes everything like easier to learn. So whoever continues this project is able to pick up where I left off or do further research based on the project. This project made me learn more about the different frequencies and intensities of our galaxy I was very unaware of. I was happy to get the opportunity to work with Dr. Hassel. He's been a great help. Any issue, he was always there to respond and give me like the route to go. So I was very thankful for that. And thank you guys for listening.